We're going to go through about 8 out of 20 of your review problems. There is a lot there, but it's more than enough preparation for your final quiz, which I hope that you only have to take once. So, you should have this calculation review in front of you. We're going to start off with number 2 here. So, first thing we want to know is what we're being asked is to find the distance between two objects. So before we write down anything that we're given, let's write down what we want to find, the distance. So we're going to keep thinking of distance as an r, a radial distance, because our objects are moving in circular paths. Most motion is elliptical, but for now we're going to treat our objects as circular, which means we're going to always think about our tangential velocity, meaning the velocity at any given instant in its orbit, as always being equal to the orbital velocity. So just to simplify things for you, both on this assignment and on the quiz, those two we can pretend like they're equivalent, even though often they are not. So what we have is a force being exerted that's keeping these two objects attracting one another. So I'm just going to go ahead and make up a force. Let's say a force of, and this is a gravitational force, of 40 newtons. Whoops. So 40 newtons of gravitational force acting on two masses. One of these masses is extremely large, times 10 to the 12 kilograms, so you know that's the one that is at the center, whereas the other one will be orbiting it. So it doesn't really matter what we go with, but I'm going to go with, let's say 2.5. So we're going to call this mass 1 is 2.5 times 10 to the 12 kilograms. And we also have another mass of, and this one we're just going to keep it no more than 3 digits. So let's go with, I don't know, let's say 150 kilograms. Okay, so this is everything that's given to us. Now the equation that you would see on the board that you would want to use for this, the force of gravity is equal to Newton's gravitational constant multiplied by the product of the masses all over the square of the distance. This g being out front here, sometimes you see it up top. It doesn't really matter where you put it, but this is how I learned it, so this is how I write it. So I guess there is one other given here that we should write down, and that is the value of g. Newton's gravitational constant is equal to 6.67 times 10 to the negative 11 newtons multiplied by, you can tell what kind of units it has. This needs to cancel out to get forces. So up top we have square meters, and on the bottom we have mass times mass. That gives us kilograms squared. All right, so we're solving for r right now. And right now it's divided into this whole numerator and being squared. So first thing you want to do whenever you start out with the variable that you're trying to solve for in the denominator position is you have to get it out of there by multiplying it on both sides. This is old news. So that cancels that out. Our next step is going to show us the radius squared multiplied by the gravitational force equals the product of Newton's gravitational constant multiplied by mass 1 multiplied by mass 2. So we're trying to find the radius. Right now it's squared and multiplied by the gravitational force. So we divide by the gravitational force on both sides. And that gets us one step closer. The radius squared equals Newton's gravitational constant multiplied by the product of the masses divided by the force of gravity. And finally, to get rid of this exponent, take the square root, and that gives us our final equation. The distance between these two objects is going to be equal to the square root of Newton's gravitational constant multiplied by the product of the masses, all divided by the gravitational force. Okay, that was the easy part, because you see here we are working with exponents. So let's first plug all of our numbers in. If you can get this far, it's just arithmetic, but you also have to understand how your calculators work or remember some of the rules of arithmetic operations when dealing with exponents. So it sounds worse than it actually is, but we'll practice it. It is something that I want to make sure you know how to do before you walk out of here. So we have meter squared on top, kilograms squared on the bottom. This whole thing's multiplied by the masses, 2.5 times 10 to the 12 times 150. Oh, forget my units. All divided by 40 newtons. And don't forget, this square root goes over this whole thing. Okay, so if you have a fancy calculator, you could plug this whole thing, the square root, it would give you some parentheses. You could go all the way through. This whole top part would have to be in parentheses though before you divided it into this. Actually, that's not true, but forget about what I just said. So I want to talk about how to work with just multiplying all of this stuff up top first, and actually we'll deal with this last. So what I want to do is just look at the arithmetic of multiplying 6.67. We're forgetting about the units. This is more of a math lesson at this point than it is a physics lesson. 6.67 multiplied by 2.5 times 10 to the 12. Alright, so hopefully you remember what to do here. We are going to take our coefficients of 6.67 and multiply them together. 2.5. This we actually need a calculator for. Everything else, other than when you get to here and here, you can do with your fingers. So multiplied by 10 to the, now we add our exponents. So we have negative 11 plus 12. Alright, so let me go down on the page a little bit. Alright, so 6.67 times 2.5, that's not that bad. 6.67 multiplied by 2.5 equals 16.675. So right here, 16.675 multiplied by 10 to the negative 11 plus 12 is just going to be 1, which gives us this whole thing times 10, which gives us 166.75. That's all. So notice all you had to do, the only actual calculator work that you had to do was multiplying these two up front. Adding the exponents, that's not that bad. Hopefully this isn't hard for you. Alright, so let's rewrite this over here. R equals the square root of, so I dealt with this and this. Now I have 166.75 newtons times meters squared divided by kilograms squared. Actually, I canceled out this right here because this was kilograms and this had one of the kilograms in the bottom canceled out. So this canceled out with this. So I'm multiplying this product by 150 kilograms. And then I divide all of that by 40. And this whole thing is in this square root. That's a common mistake people make. They forget to square root the whole thing at the end. All right, so 166.75 times 150. Don't forget your units. Not that you need it, but it helps me. So let's multiply this by 10 first. That's what we did when we said times 10 to the 1. And then we multiply this by 150. Okay, 25,012.5. So let's rewrite this one more time. Actually, probably two more times. So this is going to cancel out with this and this. I had 25,012.5. I still have a newton times a square meter. All divided by 40 newtons. Okay, so now we're going to deal with this division here. So 25,012.5 divided by 40. So I take this, divide it by 40, and I get 625.3125. So I still have my parentheses here. 625 point, I believe it was 3125. So let's check out our units here. This cancels out with this. I have square meters in here. Okay, last step. We're going to take the square root of this. Our square root is going to cancel out our square meters to just leave us an answer in meters, which is how we should be measuring our distances. So just the last step is to take the square root of this. Alright, so that's not going to do it for me. Oh, we got the answer button here. So the answer is set to whatever that last thing was. You can just write it down and then do it over again if you want, but this should work for us. And we get 25.006. Alright, so I'm going to round, and I should mention it now, 25 meters. On your test, because this number right here is prime, I was unable to make it so that all of your integers could be answers. So whenever you see, I tried very hard to get it as close as possible to an integer, but whenever you see these 2 zeros following your answer, and we just got lucky on this one, just use the whole numbers. So if you have 25.00, you got the correct answer, at least for this one. But for a lot of other problems, if you see a 0.00, then pretend as if you calculated an integer answer. All right, so let's review what we did here. A lot of work. Wrote down all the givens, especially the constant, selected the proper formula, did the algebra to isolate the unknown, what we're solving for, plugged in our numbers, dealt with the scientific notation, multiplied these two numbers out front, added together our exponents, and then just followed the orders of operation. Notice I always write my units and show how things cancel out, because if they don't come out to be in the units that you're solving for, that's how you know that if you backtrack, you might have made a mathematical mistake. All right, believe it or not, this is one of the easier ones that you're going to be exposed to. So we've been doing this for a while now. Hopefully it's not that bad. Okay, let's move on. Okay, the next problem, we're not going to have to do any algebra, but the arithmetic is still pretty rough. So we're going to move on to number 4. An object with a mass of blank times 10 to the 11. So let's just pick a random number out here. An object with a mass of, let's say, 5.67 times 10 to the 11 kilograms. Has another object orbiting it that is on average a distance of blank meters away from it. So let's just say 5 meters is our average distance. So that's pretty close for a mass this large to have another mass orbiting it at only 5 meters on average away. That's going to give us a pretty small number for what we're calculating, which is the period. So find the orbital period. So what we want to know is this right here. All right, so I hate to just throw formulas at you. I'd rather show you how they're derived, but this one is pretty rough, so I'm just going to have to give it to you. So the orbital period of one object orbiting another is equal to the square root of 4 times pi squared multiplied by the cube of the radius divided by Newton's gravitational constant multiplied by the mass of the, and then usually we call this star, the mass of the star, because right now we're finding the orbital period of the planet that's orbiting the star. So this t right here, this is the orbital period of something going around this mass right here. All right, so 4 pi, those are constants. G, those are constants. All we really need that could vary the distance of the object to the star and the mass of the star. It doesn't really have to be a star, but usually that's how this formula is used. How long does it take, like what is a year for that object? How long does it take to make one revolution? Okay, so just plugging numbers in here, but once we get to that point, it's going to be much more difficult. 4 times. So for pi on this test, in order to get your answers as close to an integer as possible, we are going to treat it as 3.14. Now it goes on infinitely, but to save ourselves time and space, we'll just round off to 3.14. Multiply by the radius, 5 meters cubed, divided by Newton's gravitational constant, so 6.67 times 10 to the 11. Oh, that's negative 11. Newtons times, what do we got? Oh, meters up top, kilograms on the bottom, multiplied by the mass of the star, which is 5.67 times 10 to the 11 kilograms. All right, so normally this is centered over here, but we got a pretty large denominator. So first thing that we should do, I mean, you could work with the top first if you wanted, but I think we should deal with this denominator. It's pretty scary looking, but again, not that bad if you remember what to do with these things. So we have to say 6.67 multiplied by 5.67 times 10 to the negative 11 plus positive 11. All right, so let's go to our calculator. 6.67 times 5.67. So that equals 37.8189. 37.8189 times 10 to the negative 11 plus 11 is 0. Anything to the 0th power is equal to 1, and 1 times anything is itself. So we've already dealt with all this right here. Alright, so now we can rewrite all of this. We have 4, let's just deal with multiplying this stuff out right now. 3.14 squared. You could have also pressed this and then to the 2. So that equals 9.8596. No units. And then 5 meters cubed. So 5 times 5 times 5. Well, 5 times 5 is 25, and 25 times 5 is 125 cubic meters. And then we divide that all by what we have down here, 37.8189. Now let's look at our units here. Our kilograms canceled out with these square kilograms. So we have newtons times square meters divided by kilograms. Alright, in order to get our answer in seconds, which is what we would want, we'd have to decompose a newton into what it is, which is a kilogram multiplied by a meter divided by a square second. These square seconds move up top right here, and then they get the square rooted to leave seconds. These meters multiply with these square meters to give you cubic meters to cancel out with these cubic meters, and these kilograms cancel out with these kilograms. So all you're left with is seconds, and they go up top because they're in the denominator of a denominator, and then they get square rooted. So take my advice for it. I don't want to do all of the dimensional analysis. Let's we know that we're going to have seconds squared after I cancel everything out, but let's deal with all of this. So I need to multiply that last number by 4 and times 125. So times 4 times 125 gives us 4,929.8, and then we divide that by 37.8189. Divided by 37.8189. Alright, so I'm not going to write that whole thing down. Let's just say, let's round it to that 0.35. So the square root of 130.35, now like I said before, when I just plug this in here for this, these cancel out. This times this is meters cubed. Meters cubed cancels out with these meters cubed. I'm left with second squared in the denominator of a denominator, which puts it in the numerator. So I have second squared here. So all I need to do now is take the square root of this number, and I'll get an answer in seconds, because the square root of square seconds is just seconds. So last step, square root at the answer key. See that here, and we get 11.4, let's say 2 seconds. So you're not going to have decimals, or if you do, these will both be 0 if you did everything right. But let's just round up to 11.41 or 11.42 seconds. So let's think about this answer for a second. If I have an object only 5 meters away from an object with a mass this large right here, it's only going to take 11 seconds for it to make one lap. So that's because it's very close and because this object is very large. Okay, moving on. So the next one that I'm going to do isn't as bad in terms of the arithmetic, but I wanted you to see that stuff because you will have to do it, and we have been doing it all this year. So now I'm going to move on to number 7. Calculate the centripetal force exerted on blank kilograms of mass. So let's keep our numbers simple this time. I'm going to go with 8. Well, first let's write down what we want to know. We want to know what the centripetal force acting on this object is. We do know that our object has 8 kilograms of mass. This is the mass of the object that's moving in a circular path acted upon, or that has the centripetal force acting on it. Moving with a constant speed of, so constant speed means it must be keeping a constant distance, otherwise it would be faster when it was closer. This constant speed, let's say 6 meters per second. So right now we're going to pretend like, well, since it's a constant speed, it's got to be circular, but our orbital rate of velocity is the same as our tangential. And we said that it's going to be 6 meters per second. And then the radius that it's moving around, let's say 22 meters. So even further from the last problem. 22 meters. Oh. Not again. Okay. All right, so we need to do a couple things here. We need to do some substitution, some derivation. Let's write down what we know. What will be on the board here is the formula for the centripetal force, which is mass times the centripetal acceleration. Now we do have the mass, but we don't have the centripetal acceleration. Let's write down the formula for centripetal acceleration. Do we have those things? Yes, we do. We have the velocity. Normally this is tangential velocity. Right now, since it's moving at a constant speed, they're both the same, just like the rubber stopper in your centripetal force lab, divided by the radial distance. So all we have to do is substitute what the centripetal acceleration is equal to with this quotient right here. So we're going to combine these two formulas. The centripetal force equals the mass multiplied by the square of the velocity divided by the radius. Okay, pretty simple. I just replaced this with what it's equal to give you this right here. All right, now we're just plugging numbers into a formula that we derived. So our mass is 8 kilograms. Our velocity is 6 meters per second. Now here's where it gets tricky. Remember, you're only, and then let me back this up a little bit. Do brackets. I don't know why it does that. Come on, please don't do it to me. So what I have in here is the speed squared. So make sure that you put that speed in parentheses and then square on the outside of the parentheses. It's really easy to make a mistake when you just put that square there. It might look like it's next to the seconds, and then it looks like you have an acceleration rather than a velocity that's being squared. And our radius, we said, is 22 meters. So you can do larger parentheses or you can do the little dot here. It doesn't matter. This is just my notational preference. All right, so let's work with what's going on inside of this bracket first before we deal with anything else. So before I worry about this, I'm going to deal with this. 6 times 6, and now I actually don't need the brackets anymore. 6 times 6 is 36 meters squared divided by seconds squared. And we're going to divide that all by 22 meters. Whoop. All right. So this quotient right here, it doesn't matter. You could say 8 times this and then divide by that. I'm going to divide these two first. So I still have my 8 kilograms out front. 36 divided by 22 gives me that, so 1.63 repeating. And let's look at what happens here. Our meters here cancel out with our square meters here, and we're left with a meter divided by a square second. Now all I need to do is multiply these two numbers. So 8 times 1.63 repeating. So I'll just multiply this by 8. The order of multiplication does not matter. And you get 13.09 repeating. Now let's look. We have a kilogram multiplied by a meter divided by a second squared. Hopefully this reminds you of the units that we should know named after somebody. We're dealing with forces. So a kilogram times a meter divided by a square second. When 1 kilogram of mass changes its speed by 1 meter per second in the time of 1 second, that's giving you the units of force, also known as a Newton. Okay, not too bad. Now we're going to do number 10. So an object orbits around a mass of blank times 10 to the 14 kilograms. So let's say, let's go with 2.8. At a distance of blank meters, let's make it a larger distance this time. Let's say 825, or I guess 56 meters. And then finally, calculate the velocity the object would need to have in order to escape its orbit. So there's a new quantity. This is known as the escape velocity. So this is not the velocity of Earth. This is the velocity needed to escape the gravitational pull. All right, so we're going to calculate exactly what velocity it has to have in order for its kinetic energy to exceed or actually be equal to its potential energy. So in order for this to be true, the kinetic energy has to be greater than or equal to the potential energy. So I'm going to show you how to derive this formula. I'm going to give it to you on the day of the quiz, but I want you to see it right now. So to calculate the escape velocity, we need to know exactly how fast it needs to go in order or once the kinetic energy reaches the potential energy, this is possible. So this is the stuff that's old that you're not going to have to know, but you should be able to follow along with this. We all know kinetic energy is equal to this. Now the potential energy is equal to mgh, but hopefully you remember that mg is actually just equal to the weight. Oh, this should say A right here. This g right here, this is equal to the gravitational acceleration. It's just a specific type of force. But instead of writing m times g, I'm actually going to write force this time, or instead of writing weight. Because we're dealing with the force of gravity and we have a new formula for that. And this h right here, we'll go ahead and write h right now, but matter of fact, I'm going to go ahead and write r, because we're talking about how far away something is in orbit. You know, it's escape velocity in order to escape its orbit. So we're dealing with r. I could have written d, h, or r. It's all a measurement of distance. So I'm going to make one more substitution here, and that is for force. The force is not just equal to mass times acceleration, or mass times gravitational acceleration. It's equal to Newton's gravitational constant multiplied by the product of the masses divided by the radius squared, and then I'm multiplying that by the radius. So this whole thing right here was replaced by this whole thing right here. I believe in the last video I showed you that g is equal to all of this right here. Newton's gravitational constant multiplied by mass divided by the square radius. So m, and then this is all g, and then h, or now we're talking about r. All right, so let's do the algebra now. This is going to cancel out with this first. So we just have r. Now we need to decide whether this is mass 1 or mass 2. It doesn't really matter. Since this kinetic energy right here, this is the object that's in motion, a lot of times mass 1 could be the mass of the star, or mass 2. Doesn't matter. Let's just say, we're going to say this is mass 1, so this is mass 2. So when I multiply, or when I do the algebra, I multiply by 2 here, multiply by 2 here. That gives me m2v squared equals g times m1 times m2 divided by r. So then I'm going to divide by m2 on both sides now. That cancels that out. These two cancel each other out. Square the velocity is equal to g times one of the mass that's in motion around the other. Or no, I'm sorry, I got that switched around. It's the mass of the planet, the larger mass. So this mass 2, this is the one that's in motion. This mass 1, this is the object that's keeping the other one in orbit until it reaches this velocity. And then we still have this r here. So one final step, take the square root, and the escape velocity, now we should call it, is going to be equal to the square root of Newton's gravitational constant multiplied by the mass that the planet is orbiting divided by the radial distance. So notice, in order for an object to escape the orbit of another, it doesn't even depend on its own mass. It only depends on the mass of the object that it is orbiting. So we have the radius, we have the mass, and we should know Newton's gravitational constant. Now we're just plugging numbers into the formula. So 6.67 times 10 to the negative 11 newtons times meter squared divided by kilogram squared multiplied by, up top here we have 2.8 times 10 to the 14 kilograms divided by 856 meters. Okay, so we need to work with this stuff here. Let's just bring this scientific notation. 6.67 times 10 to the negative 11. We're just going to deal with the numbers. Forget about the units for now. Multiplied by 2.8 times 10 to the 14. So we'll deal with these numbers out front and then these numbers second. So 6.67 times 2.8 times 10 to the negative 11 plus 14. Alright, so we only need the calculator for this part. 6.67 times 2.8 equals 18.676 times 10 to the negative 11 plus 14 is 3. And then last thing I'm going to do, might as well multiply this through right now, times 10 to the 3. It's like saying multiplied times 1,000. Or you can just look at, I'm going to move the decimal place this number of times. So 1, 2, 3. So I'm going to get finally 18,676. So let's rewrite this now. All I did was multiply these two numbers. So this cancels out with this. I have 18,676 newtons times square meters divided by kilograms. And then all this whole thing is over 856 meters. Alright, so forget about the units for now. Let's just deal with the math. So this number here divided by 856. So let's multiply this by 10 to the third. Show you that it comes out to be the same as multiplying it by 1,000. And then we divide that by 856. We get 21 point, let's say 82. So the square root of 21.82. So let's look at our units here. I know that this is going to cancel out here with this. Now what is a newton equal to? It's a kilogram times a meter divided by a square second. Now I'm multiplying this by a meter, and I'm dividing this whole thing by a kilogram. So notice this whole thing, this is just n. This is the meter because this canceled out with the square meter. So this times this is square meters, but this is canceling out with this. So a meter times a meter is a meters squared divided by seconds squared. Alright, last step is to just take the square root of 21.82. So the square root of our answer gives us 4.67. So not a very fast velocity, 4.67. And then a square meter turns into a meter because we're square rooting it, and a square second turns into a second. All right, so let's recap, and let me tell you where you're going to have to start. Obviously, you're going to have to start with this, but you are going to be given this equation here. I will not force you to derive the formula for the escape velocity, but I did want you to see it. This idea of the kinetic energy has got to be greater than potential, that makes sense. Its energy of motion has to be larger than the energy of position. What's holding it in place has to be weaker than what keeps it, or than what makes it move, and it's going to move out of that position that it's held, which is an orbital path. So we substituted, we said, all right, if it's going to be equal to it, that's the minimum amount necessary to exceed that energy holding it in place, right? Greater than or equal to. That means it has to be larger than this value. Anything larger than this and it will escape its orbit. So we set those two equal to each other. M and G is the same as force. Force is the same as this formula right here. We did the algebra. What we came out with is the escape velocity is the square root of Newton's gravitational constant multiplied by the mass of the object that this mass, this is not the mass of the object that is in orbit, that's this one. This is the mass of the object that's keeping it in orbit. Here's how far away it is, plug everything in, and here we go. So you will start with this. You might have to do some algebra to calculate the radius or the mass. Obviously you won't have to calculate this, but it's not going to be that tough. So next problem is going to be pretty tough though. In fact, from here on out, actually there's one more that's pretty easy, but we're only halfway done with the ones that I'm going to go through. So this video is not going to be one class period long. You're going to have to finish it on your own at home. So we're going to move on to the back side of this paper, number 13. The gravitational force supplies the centripetal force. So that right there tells you something that's noteworthy. The force of gravity is equal to the force, or the centripetal force. So remember, the centripetal force keeps objects changing their path. It's what makes something move around in a circle. And the force of gravity is attractive. It's what's pulling something around that circular path. So, you could think about a planet and a star, but the force of gravity is what's pulling it forward. Objects want to continue to move in their direction, so the centripetal force makes it curve around, because the object's inertia combined with the force of gravity gives you that centripetal force, accelerating it in a curved path. All right, so the centripetal force supplies this, or the gravitational supplies the centripetal force to keep a mass orbiting another mass of blank times 10 to the 15 kilograms at a distance of blank meters. Find the orbital velocity. All right, so the larger mass is going to be something times 10 to the 15. So this is a given right here, but first let's write down what we have. So let's go with 7.62 times 10 to the 15. This is the mass of the larger object, so I'm going to make that mass 1. And we have to put it at a distance. Let's make our distance 544 meters. So here's how far away it is. Here's the mass that's at the center. This is how far away the object is, which is orbiting it. So we're not given much information here. Only how large the mass that's keeping it in orbit and how far away it is. But what we can do is write down what these are equal to and set them equal to each other. So let's do that. Force of gravity is equal to Newton's gravitational constant multiplied by mass 1 times mass 2. This is the mass that's in orbit. This is the mass that's keeping it in orbit. The radial distance squared. This is how far away these two masses are. And we know that the centripetal force is equal to the mass of the object that is in orbit. That's the one that's moving, multiplied by the centripetal acceleration. Now, let's take a step back and look at what are we being asked to find. We're being asked to find the orbital velocity. Right now, neither of our equations have the orbital velocity in it. But one of those has a formula for it. Now this is normally the tangential velocity, but we can pretend like our object is moving in a circular path so that the orbital velocity is equal to the tangential velocity. So we have a lot of substitutions to make. We need to substitute this in here, which we've already done, and we need to set these two equal to each other. So there's going to be a lot of physics, or a lot of substitution and algebra here. Let's start out by writing what we wrote down first. We know this is equal to this. Well, since this is equal to this, and this is equal to this, this whole thing is equal to this whole thing. Newton's gravitational constant multiplied by the product of the masses divided by the square of the radial distance must be equal to the mass of the object in orbit multiplied by the centripetal acceleration. Alright, almost ready. Now we need to substitute this for this. And then we can start the algebra. Alright, so keep in mind we're trying to solve for v. Right now v is squared. It's divided by the radial distance between these two masses, and it's multiplied by the mass of the object that's being curved in a path from the attraction of this object and its own inertia. So first thing I would say to do, get rid of this r by multiplying it on both sides. So I need to multiply it over here too. So that's going to cancel that out. This r is going to cancel out with this r. And we're left with Newton's gravitational constant times the product of the masses divided by just the radius, because this r canceled out with the r squared, equals the mass of the object in orbit times the velocity of that object. We're looking for orbital velocity. This is tangential, but we'll treat the two as the same. So trying to get this alone, divide by the mass of the object in orbit on both sides. I can just put it in the denominator because then it's being divided into this whole thing. These two cancel out, these two cancel out. The velocity of the object in orbit is equal to Newton's gravitational constant multiplied by the mass that's dragging it around in orbit divided by the radial distance. Okay, and then the last thing is to take the square root. This should look familiar from what we just saw last time. The escape velocity. So mathematically, we treat them as the same, but algebraically came at them from different angles. So let's plug our numbers in now. I'm just double checking something here. Okay. All right. So Newton's gravitational constant, 6.67 times 10 to the negative 11 newtons times meters squared divided by kilograms squared times the mass of the object that's keeping in orbit, 7.62 times 10 to the 15 kilograms divided by 544 meters. All right, so let's work with just these scientific numbers first. So multiply these two decimals first. Then work with your exponents, times 10 to the negative 11 plus 15. So we can go to the calculator for this, 6.67 times 7.62. $50.8254 times 10 to the negative 11 plus 15 is 4. So we're going to move our decimal place 1, 2, 3, 4 times to just get 508,254. So that's what happens when we multiply these two through. So the velocity of this object is going to be 508,254. Our kilograms cancels out with this. So we have a Newton, or we canceled out the square kilogram, sorry. Newton times a square meter divided by a kilogram, all divided by 544 meters. All right, so let's divide those two through. Multiply this by 10 to the 4 divided by 544 gives you 934.29. And this is in, or square rooted, 934.29. So I could go through all the dimensional analysis again, but I just did it in the last problem. So all we need to do is take the square root of that last number, and we get our velocity, 30.567. All right, so very similar as the last problem. Not too much of a difference. Just to kind of ended up at the answer or at the formula from a different path. Okay, so now we're going to move on to number 15. It's been an hour now, so you're definitely, if you didn't start watching this last night, you're going to have to finish watching it tonight. But it's been up since Sunday night, so hopefully you accessed it before the last minute. Okay, looking at 15. Calculate the centripetal force accelerating blank kilograms of mass. So let's just start by writing what we're being asked to find. We want to know what the centripetal force is. and we're given a certain amount of mass. Wait a minute, am I doing the right problem? Number 15, accelerating blank kilograms of mass to orbit at a radial distance of blank meters in a period of blank seconds for each revolution. Okay, yeah, I do want to do this problem. Just got things switched around here. Okay, so this is a tough one. This will probably be the toughest problem we do here. So the mass, let's go with, well, let's go with 460 kilograms. And then, sorry, I got a little thrown off by the order of the questions here. It's at a radial distance of, oh, we need a large distance here. So let's say 6.4 times 10 to the 5. And then finally, a period of how many seconds here? Let's say 14,080 seconds. So this is how quickly or how long it takes for it to make its way around. All right, so this mass, this is the mass of the object that is in motion. Okay, so it's not too straightforward how to solve this problem. It's almost like we should just write down every formula that we have with all of these values, with the masses and the radii and the periods. But let's start with what the centripetal force is equal to. We know the centripetal force is equal to the mass of the object in motion, which we have here, times the centripetal acceleration. Now we don't have the centripetal acceleration, so let's write down that formula first. The velocity squared times the radius. Now we don't have the velocity squared, but what problem on the board, what formula on the board has velocity in it? The orbital velocity is equal to 2 times pi times r divided by the period. We do have r, we do have the period. So we're going to need to replace v with what we know that v is equal to. And then we're going to have to replace a sub c, the centripetal acceleration, with what that is equal to. So let's do this one step at a time. First, the centripetal acceleration is equal to the mass. And instead of writing this, we're going to write this, v squared divided by r. Now here's where it starts to get really tough. We have to plug in v squared for this whole thing right here. So it's about to look not so great. So we're going to replace this whole v with 2 pi r divided by t all squared. Oh, and I left the mass out. So I'm just going to put it on this side. It doesn't matter if it's on this side or this side. Okay, so this is where we start. Now we can start to, I guess, multiply this whole thing by itself. So let's work that out. Don't forget my mass this time. So 2 squared is 4. times pi squared times the radius squared, all divided by the period squared. So this whole thing is the numerator, and we divide that by the radius. So I know that this is hard to look at, but in a second it's not going to be too bad. So let me just show you what this looks like when we simplify it. I'm just dealing with this fraction on top of a fraction. So 4 pi squared times r squared divided by t squared. If we're dividing this whole thing by r, we're really just multiplying it by the reciprocal, which is 1 over r. So we're going to change this into 4 pi squared times r squared divided by t squared divided by r, and then this cancels out with this, and we get 4 pi squared times r divided by t squared. That's this whole thing right here. So now I'm going to rewrite what the centripetal force is equal to. Mass times 4 pi squared times r divided by t squared. Now we have a formula that contains the mass, which we're given, the radius, which we're given, and the period, which we're given. Okay, so just to review what we had to do, replace a sub c with what it's equal to, and replace v with what it's equal to. And then we wanted to simplify this. You could plug the numbers in right here and do all the math, but I wanted to just show you how to kind of cancel some things out so that you could stomach looking at this a little bit easier. It's still not that great looking, but okay, so our mass is 460 kilograms. I'm going to put this in brackets now. 4 times 3.14 squared times our distance, 6.4, times 10 to the 5 meters, all divided by 1,480 seconds. All right. So 460 kilograms. Now let's deal with this numerator. It's not that bad. So 4 times 3.14 squared times, so let's just plug this into the calculator as we go through. 4 times 3.14 squared times 6.4 times 10 to the 5. 6.4 times 10 to the 5. So this is our whole numerator right here. 20, let's see this, 2,524,576. So this is 2,524,576 meters. Whoops. And then we're going to divide this by, oh, I forgot to square this, 1,480 seconds squared. So let's deal with that first. 1480 squared equals 2,190,400. 2,190,400 seconds squared. All right, almost done with this one. This is the most painful one by far. So we need to multiply this whole thing through. So 460 multiplied by 2,524,576. 2,500 and whoops 24,576, and then we divide that by 2,190,400. And we get a pretty manageable number, 530.18. Now this is a kilogram times a meter divided by a square second, or a Newton. Okay, that one was pretty rough. This is definitely the hardest problem on the test. I think that the hardest part is once you substitute this, you have to square a fraction, both the top and the bottom. Just every single one of these things needs to get squared. And then having a fraction within a fraction is a, pain. So once you get to this point, if you want to just plug all the numbers in, you can. But I think it's easier if you just, if I'm dividing by something, I'm multiplying by the reciprocal. That allows you to simplify things to make it look a little bit better than what it does over here. But you do have to substitute twice, which is what makes it twice as hard as the rest of them. Okay, moving on. So now we're going to go back to the one that I thought we were just doing, but I switched up the order of the questions and I didn't make that note in my notebook. Now we're going to do 13. So the gravitational force supplies the centripetal force to keep, oh wait, no, we're doing 15. Calculate the centripetal force acting on blank kilograms of mass. So let's first write down what we want to know. We want to know the centripetal force. Wait a second here. I messed up the question again. I think we just want to do 19 and then 20. Yeah, we just did 15. Sorry. Okay, a mass of blank times 10 to the 4 kilograms. So this one's relatively simple. Okay, so the first mass, the mass of blank times 10 to the 4 kilograms orbits another. So we're going to say mass 1 is the one that's in orbit. Blank times 10 to the 4. Let's just say 3.2 times 10 to the 4 kilograms. That orbits another mass, so mass 2. You know what, and here's some good notation to remember. The smaller mass, forget about this 1. We use a lowercase m. The larger mass, use an uppercase m. You'll often see that, and it will help you distinguish, okay, this is the smaller one, this is the larger one, this is the one that keeps this one in orbit, this is the one that orbits this one. So this one has a mass of something times 10 to the 16, let's say 2.5 times 10 to the 16 kilograms. Okay, and then at a distance of blank meters, so let's go with 250 meters. Okay. Calculate the centripetal acceleration supplied by gravity. All right, so a little jump that you have to make here. You know that acceleration is what you're looking for. But you should also know that you can never have acceleration without a force. So it must be the centripetal force. And in this case, gravity is supplying that centripetal force. So being able to make this jump just based off of your understanding of the question is an important part of this process. So the centripetal force we know is equal to the mass of the object in motion. This is mass 1, or the smaller mass, multiplied by the centripetal acceleration. That's what we're solving for. And that's equal to, well, we won't jump there yet. Force of gravity, Newton's gravitational constant, multiplied by the smaller mass times the larger mass divided by the distance between them squared. Now, since we know that these two are equal to each other, we know that this is equal to this. So the mass times the centripetal acceleration equals Newton's gravitational constant multiplied by the one in orbit times the one that it's orbiting, the mass of the two, divided by the radial distance. All right, so here's where lowercase m and uppercase m come in handy. Remember, we're solving for this, so I just divide this on both sides. These two are going to cancel out. The centripetal acceleration is going to be equal to Newton's gravitational constant multiplied by the larger mass, so we didn't even need the smaller mass, divided by the radial distance squared. So this is a tricky problem. One, because you have to know, one, because I'm giving you information that you don't need, and two, because I'm not telling you that the forces are equal. I'm telling you that gravity supplies the centripetal acceleration. But you're not going to have centripetal acceleration without centripetal force, and since gravity is what's accelerating it, that means it's equal to the centripetal force. All right, so the centripetal acceleration is equal to, oh great, 6.67 times 10 to the negative 11 newtons times meter squared divided by kilogram squared multiplied by the mass of the object, 2.5 times 10 to the 16 kilograms divided by the radial distance squared, which is 250 meters. All right, so let's work with our arithmetic. 6.67 times 10 to the negative 11 multiplied by 2.5 times 10 to the 16. We're only going to worry about our coefficients here out front. So 6.67 times 2.5, and then we multiply that by 10 to the negative 11 plus 16. All right, so 6.67 times 2.5 equals 16.675 times negative 11 plus 16 is going to be equal to 5. So we're going to move our decimal place over 5 times. We got 16,675, 1, 2, 3, 2 left over, 0, 0. So let's rewrite this. Kilograms cancels out with these square kilograms. 1,667,500 newtons times square meters divided by kilograms, all divided by 250 squared. and that gives me 62,500. Square meters. That'll cancel out with these square meters here. So first I need to divide 1,667,500 by this 62,500. So this is way easier. 1 million, all right. 1,666,500 divided by, and then I can just put my answer in then, because that's what's left over from the memory, and I get 26.68. All right, so down here, 26.68, and then a Newton divided by a kilogram. Well, a Newton is a kilogram times a meter per second squared, so this cancels out with those kilograms, and you're left with a meter per second squared. Okay, so we're going to do one more problem, and it's the last one. But so that my computer doesn't die in the middle of that problem, and so that I don't have to stop this video, you're going to have to wait for me to go get my charger. So there's going to be some dead air here for a second. All right, back on the mic. So one more problem. Number 20. If an object keeps a constant speed of blank times 10 to the 5 meters per second. So let's write that down first. Constant velocity of, I'm going to go with, let's say 7.2 times 10 to the 5 meters per second. As it is curved around a path by the centripetal acceleration of blank meters per second squared. So I'm going to give this a very large centripetal acceleration since it has such a large tangential and orbital velocity. Let's go with 14,075 meters per second squared. Okay, so what do we want to know here? What is the object's orbital period? So we want to know what t is equal to. All right, so what formulas do we have? We don't have the formula that we have with t in it. There's a couple of them. There's a really brutal one, which I don't think we're going to need for this one. Right, we don't have any masses. I don't know if we're going to be able to get any masses, and we don't have a radius. So hopefully we don't need this one. But there is another one that we have. It's not solved for t, but it's there in the denominator. We also have a formula for centripetal acceleration, and that has a v in it. All right, so how can we combine these two? We've already done this once. We're looking for t. So I think what we should do first is just solve for t using this equation. First you want to get it out of there. v times t equals 2 pi r, and then we'll divide by v on both sides. T equals 2 pi r divided by v. Now, let me go back to why we can't use this equation over here. There's no equation for m. We could use a different equation to solve for m, but the only other one I can think of is with force, and we don't have the force up here. And we couldn't find the force, I guess, unless we found the radius, and we are going to have to find the radius. So we might actually be able to use this, but it's not going to be as easy as using this one. So we want to use this equation. We have v, we know 2 and pi, but we don't have r. However, we do have an equation with r, and that equation contains two things that we know. So let's solve for r in this equation first. So r times AC equals v squared. Now I can divide by AC on both sides, and that gives me what r is equal to. V squared over AC. So now I don't need r. If I have v and AC, I can replace this whole thing here with r. So let's rewrite our equation over here. 2 times pi times, not r, but what r is equal to, v squared divided by a sub c, or the centripetal acceleration, over v. So there's two things you could do right now. We could simplify this algebraically, or we could just start plugging numbers in. Since we have such large numbers to work with, I think it's best that we simplify things algebraically. So let me rewrite this as 2 pi over v multiplied by v squared times a sub c. I'm just multiplying this. Instead of putting this in numerator, I'm putting it off to the side. This is just like the force equation, where instead of putting g off to the side, I could put it up top, and it would be the same exact thing. Now I'm taking this from the top and putting it to the side, right here. The reason why I'm doing that is because I want you to see that this can cancel out with this, and this gets left in the numerator. So the formula that we have for t is equal to 2 times pi times v divided by a sub c. So now we can start plugging numbers in. 2 times pi, or actually, let's plug in the number that we want to use for pi. 3.14 multiplied by our velocity, 7.5 times 10 to the 5th power meters per second, all divided by our acceleration of 14,075 meters per second squared. So let's multiply our numerator across. 2 times 3.14 times 7.5 times 10 to the 5th power. 2 times 3.14 times 7.5 times 10 to the 5th power gives us 4,710,000, and we're dividing that by 1,475. And we get 3,193.22. So 3,193.22. Let's look at our units here. My meters are canceling out these. My seconds are canceling out these square seconds. And since this second is in the denominator of a denominator, it comes up to the top, which gives me seconds. So 3,193.22 seconds. We could even convert that to minutes if I wanted to be really cruel, but we just spent 90 minutes solving problems and we only did 8 of them. So that means that this homework is going to take a long time if you are going to do it all. Now I do move slow and I did show you more than you needed to, but the last 5 problems on your test are going to be almost this hard. I actually did the hardest 2 out of each of the 4 versions on your test. So don't forget your units though. You got units for speed, units for acceleration, units for time, units for force, units for distance. Out of those 10 points, earning half of them should be extremely easy for you at this point in the year. But with that being said, this concludes this video.